Hello, everyone, and welcome to this AP Chemistry virtual lesson. My name is Michael Fairbaugh, and I teach AP Chemistry at Albemarle High School in Charlottesville, Virginia. Today, I am going to be talking to you about Unit 4, which is chemical reactions. Before I start the lesson today, I just want to remind you that students, you can visit the website apstudents.org/exams2020, and you can get more information about the online AP exam format this year. You can find information about the content, about the length of the exam, the structure and the format. So all kinds of helpful information about the AP exam will be at apstudents.org/exams2020. Before we get started, hopefully you have access to scratch paper and something to write with and a periodic table. If not, feel free to pause the video and get those materials. And if you're ready to go, let's go ahead and get started with today's lesson on Unit 4. So in this particular lesson, I will talk about topics 4.1 through 4.4, and that includes physical and chemical changes, reactions, net ionic equations, and representations, particle diagrams to represent reactions. So selected topics are listed here, as well as the science practices, including formulate a hypothesis or predict the results of an experiment, determine a balanced chemical equation, represent chemical substances or phenomena with appropriate diagrams or models, and support a claim with evidence from experimental data. So we'll talk about physical versus chemical change. We'll talk about writing a balanced chemical equation, net ionic equations, and using particle diagrams to represent reactions. For our warm-up today, let's review the homework problem that Mr. Byrne assigned in yesterday's lesson. And it looked like this. We have a graph of absorbance versus concentration. And this is for a solution of cobalt. So we have the concentration of cobalt 2+, and different solutions were prepared, and the absorbance of each solution is measured to generate this calibration plot. So we can see the direct relationship between absorbance and concentration. Part A of this question asks to figure out the concentration of cobalt in a solution if the absorbance is 0.74. So let's go ahead and just draw a line on our calibration plot at approximately 0.74 on the y-axis. And then where that intersects the line, we can trace that down to the x-axis. So estimating from the graph, if the absorbance of the solution is 0.74, then the concentration of cobalt in that solution would be approximately 0.013 moles per liter. And they would have accepted values in the range of 0.0125 all the way to 0.0135. So based on our answer to part A, let's move on to part B so we can calculate the number of moles of cobalt, the cobalt 2+ aqueous ion, in this solution that has a volume of 50.00 milliliters. Well, we know that since molarity is moles per liter, we're going to use our answer to part A as a conversion factor to convert from liters to moles. Of course, we should also know from the metric system that there are 1,000 milliliters in a liter. So if we do this as a conversion factor, we're going to take 50, divide by 1,000, and then multiply by the molarity in such a way that liters cancels out, and we have moles in our final answer. And if we do this math, I'm going to go ahead and round off my answer to 3 significant figures just based on my estimate of the concentration. I have 6.50 times 10 to the minus 4 moles of the cobalt ion. So that takes care of the answer to part B. In part C, they are asking us to calculate the mass percent of cobalt in this 0.630 gram sample of the ore. So that means that only a small fraction of that sample is actually cobalt. So we have to do a ratio of grams of cobalt divided by grams of the ore. On the periodic table, we see that the molar mass, which comes from the atomic mass of cobalt, is 58.93. So we'll take our answer to part B and we'll convert from moles to grams using the information off the periodic table. And then this answer, which is the grams of cobalt, will be divided by the mass of the ore. So we have a ratio of grams of cobalt divided by the grams of the sample of the ore, multiply that by 100%, and that will give us the mass percent of cobalt in this sample of ore. In this case, if we do this math, we get approximately 6.08% cobalt by mass. All right, moving on to the next part of the homework problem from yesterday's lesson. It says that the student in the previous problem used a spectrophotometer to determine the absorbance of each of the standard solutions at a wavelength of 510 nanometers. It also tells us that a wavelength of 510 nanometers corresponds to an approximate frequency of 6 times 10 to the 14th hertz, which is also inverse seconds. What is the approximate energy of one photon of this light? So you have access to an AP exam equations and constants sheet. Let me go ahead and show you a portion of that. And we can see that under atomic structure, there is energy and speed of light and frequency and wavelength in equations on the left, and then we have various constants on the right. So we're going to focus on the relationship between energy and frequency. Since we are given the frequency in this problem, we can calculate the energy, and they also tell us that Planck's constant is 6.626 times 10 to the negative 34 joules seconds. So we'll take our frequency that was given to us in the problem and multiply by Planck's constant, and as the seconds cancel out, we have our answer in joules. Now this will be joules per one photon. If we needed to do joules per mole, then we would have used Avogadro's number, again, which is also listed on the equation sheet. But we're just doing a joule for a single number of joules in a single photon. So this answer, 4 times 10 to the negative 19 joules, is correct. Now for the color of the light, you would have to be given more information to determine whether this was red or orange or yellow or green or blue or purple. So I'm going to give you a chart that shows you the wavelength ranges for various colors of the visible light spectrum. As you can see, 700 would be the long end of the spectrum, the longer wavelength corresponding to red light. The short end of 400 to 450 nanometers is violet light. So 510 would fall somewhere between green and blue. So the color of that light would be sort of greenish blue or cyan. All right, let's get into our lesson on Unit 4. Again, we're going to talk about physical versus chemical changes. And you probably already know this, but I'll tell you that a physical change occurs when a substance undergoes a change in properties, but not a change in composition. So one example of a physical change is a phase change. For example, the melting of ice, the freezing of pentane, the evaporation of methanol, the condensation of hydrogen chloride, the sublimation of carbon dioxide, or the deposition of iodine. As you can see in all of these phase changes, the chemical formula on both sides of the equation remains unchanged. So all we have is a change of phase. That's a physical change. Another example of a physical change would be separating a mixture. So for example, if we had a solid and we were separating it from a liquid using filtration, or if we had a mixture of two substances that had different boiling points, we might separate that mixture using a technique known as distillation, or possibly a chromatography experiment to separate two or more substances on the basis of how well they interact with a mobile phase and travel up the paper. All of these separation of mixture techniques involve physical changes. So in contrast, a chemical change involves a transformation of one substance into a new substance that has a new composition. So rather than, let's say, simply evaporating water, if we undergo electrolysis where water is transformed into hydrogen gas and oxygen gas, those substances are completely different. That would be a chemical change. Other examples might include the combination of carbon monoxide and hydrogen gas to make methanol, or the reaction of sodium metal and water to produce aqueous sodium hydroxide and hydrogen gas, or possibly a reaction between two chemicals that are aqueous, silver nitrate and sodium chloride, and we produce aqueous sodium nitrate and silver chloride. So we can have conversions of one substance to another. That's a chemical change. Now, if we think about what's happening at the particle level during physical versus chemical changes, if the only attractions that are broken or formed are intermolecular or interparticle forces, then it is likely that a physical change is occurring. For example, if we're just evaporating water, we're breaking the intermolecular forces between the water molecules. But if chemical bonds are broken or formed, then it is likely a chemical change is occurring. So here we are forming and breaking bonds as we transform hydrogen and oxygen to produce water. Now, the course and exam description describes the fact that dissolving salt in water, for example, arguments could be made for that process being either a physical or a chemical change. Chemical, because ionic bonds are broken as the salt dissolves, possibly a physical change because we are producing interparticle forces such as ion dipole forces. So the AP exam would not ask students to classify the dissolving of salt in water to be a physical or a chemical change. That's too ambiguous. So again, focusing on phase changes and simple breaking of intermolecular forces would be physical. Breaking chemical bonds to produce new substances, chemical change. The next thing I'd like to talk about in this lesson is writing a balanced chemical equation. So I'm going to give you a description of a chemical reaction, and we'll turn this into a chemical equation. Now, you don't have to memorize chemical formulas. By and large, the AP exam, when they ask you a question, they typically give both the name and the chemical formula. So if I say calcium hydroxide and you can't remember the exact formula of calcium hydroxide, they're not going to try to put a naming question along with a writing a chemical reaction. So I'm telling you that calcium hydroxide is Ca parentheses OH2, and that hydrobromic acid has the formula HBr. So we have solid calcium hydroxide reacting with a solution of aqueous hydrobromic acid, and it produces water, so H2O, liquid water, and aqueous calcium bromide. Now, on the AP exam, if you are asked to write a balanced chemical equation, in your answer, you are not going to be required to include the phase of matter, such as solid, liquid, gas, or aqueous. So I'm going to go ahead and rewrite this equation without the phases of matter, and that would still be correct. However, you should double check your final answer to make sure that each chemical formula has been written correctly and that your equation has been balanced correctly. So we have 2 bromine atoms on the right side of the equation. So we'll add a coefficient of 2 on the left. And now, as you can see, we have a total of 4 hydrogen atoms on the left and 2 oxygen atoms on the left. So we'll add a 2 as a coefficient in front of the water. And now this equation is completely balanced. All right, here's another example of a chemical reaction that we can turn into a chemical equation. We have phosphoric acid, H3PO4. It reacts with potassium hydroxide, KOH, and it produces water along with potassium phosphate, K3PO4. So considering the left side and the right side of the equation, there's a variety of ways you might consider balancing this equation. If I start with, let's say, oxygen, I can see that there are exactly 5 oxygen atoms on both sides of the equation. With respect to phosphorus, there's only 1 phosphorus atom on each side of the equation, but hopefully you can see that there are 3 potassium atoms on the right, and there is only 1 potassium atom on the left. Let's go ahead and add a 3 in front of the KOH to balance the potassiums. Now this certainly changes our total for oxygens and hydrogens. We now have a total of 6 hydrogens on the left. So therefore, if we need 6 hydrogen atoms on the right, if we add a 3, this will also give us a total of 7 oxygen atoms, and the entire equation is now balanced. All right, here's another example. We have a chemical that is undergoing combustion, and the formula of that chemical is C5H12O, and it's reacting with oxygen to produce carbon dioxide and water. Now, I bring up this particular example because it illustrates a point that some students might make a mistake, even if they are very good at balancing equations and they've done it for years and they've practiced it and they understand how to do it, they still might make a mistake either because they're not quite paying attention or they're going too fast. So I'm going to start with the carbon. I see 5 carbons on the left, so I'll balance the carbon by putting a 5 in front of the carbon dioxide. I see 12 hydrogen atoms on the left, so I'll balance the hydrogen by putting a 6 in front of the water on the right. So at this point, a student might take a look at their right side of the equation, and they might recognize that 5 times 2 is 10. This is for oxygen atoms, and 6 times 1 is 6. So there are clearly 16 oxygen atoms on the right. So they put an 8 in front of the O2 and they say, okay, we're done. Now, I'll give you a moment. Hopefully you've already figured this out, but I'll give you a moment to take a look and decide, is this equation in fact balanced? And if not, what you might do to solve this problem. Well, hopefully you can realize that we do have to count all of the oxygen. So in fact, if we put an 8 in front of the O2, we now have 17 oxygen atoms on the left side of the equation. So we'll have to solve this problem by getting exactly 16. So this is how I might do it. And I might use 15 over 2 as a fraction, or 7.5. Now at this point, the equation is balanced because we have a total of 16 oxygen atoms on each side. And depending on the specific information given to you in the question, this might be your final answer. Now, if they go on to say that you should balance this equation using lowest whole numbers, and you can't have a fraction for a coefficient, you just go back to each and every coefficient and multiply by 2. So the coefficients might be, instead of 1, 7.5, 5, and 6, multiplying by 2 might give us coefficients of 2, 15, 10, and 12. And of course, the equation is now still balanced. If the equation said, write a balanced chemical equation for the combustion of exactly 1 mole of C5H12O, then the top equation would be considered correct, and you'd be allowed to have a fractional coefficient. But if they say balance the equation using lowest possible whole numbers, then you'd want to use the bottom version of this equation. All right, here's another example of a chemical equation. This involves magnesium nitrate, so Mg parentheses NO3, 2. It reacts with sodium phosphate. Sodium phosphate is Na3PO4. And the products of the reaction are sodium nitrate, NaNO3, and magnesium phosphate, Mg3 parentheses PO4, 2. And I would call your attention to the parentheses because some students might balance this equation in a way that might make it more work for themselves. So yes, if you look at, let's say, oxygen for a moment, there are 3 oxygen atoms with the sodium nitrate. And since 2 times 4 is 8, we have another 8. So trying to balance the individual oxygens might be problematic because oxygen is featured in each and every formula. So I would say it might be easier to balance the NO3 and the PO4 as one group of atoms. Might be easier to go ahead and attack it that way. So I see 2 PO4, 2 phosphate ions on the right. I'll definitely want 2 phosphates on the left. And then over here, I could consider what's going to happen if I end up with 3 magnesiums and I have 3 magnesiums on this side. That's going to give me 6 of the nitrate ions. So balancing it might be easier than thinking of it as 18 oxygen. So I'm going to go ahead and put a 3 in front of the magnesium nitrate to balance the magnesium. I now have 6 nitrate ions. I have PO4 multiplied by 2 on the right. I'll go ahead and get the 2 as a coefficient on the left. And now I have 6 sodiums. So 6 sodiums and 6 nitrates. The equation is balanced. Again, a variety of ways to balance an equation, but sometimes if you can balance polyatomic ions as a group when they appear on both sides of the equation, that might be a little bit easier than the individual atoms. All right, let's move on from writing a balanced chemical equation to net ionic equations. A sample of solid calcium chloride is dissolved completely in water. When this solution is tested for conductivity, it is observed that it does conduct electricity. Write the net ionic equation for the dissolution or dissolving of calcium chloride into water. Now, when a student first sees this, calcium chloride and water, this might be how they envision it. Now, the problem with writing the reactants as calcium chloride plus H2O is it might lead you down the path to assume that somehow water is reacting with the calcium chloride to produce other substances such as hydrogen or hydroxide. So it turns out that when an ionic solid dissolves in water, unless you're given more specific information about acid-base properties, or you recognize something that would normally happen in terms of acid-base chemistry or oxidation reduction, we can assume that an ionic solid that is simply dissolving into water would just break up into aqueous ions. And so therefore, the water is not itself a reactant, but rather the medium in which the calcium chloride dissolves. So I'm going to go ahead and write calcium chloride on the left, and then that's it. I will show calcium and chlorine on the right side of the equation. Now, a student might write this because they want the formula to be broken up. However, these are the symbols for the elements, not the ions. Remember that calcium chloride contains calcium ions and chloride ions. Some students will stop here. So remember that while these are the correct symbols and charges, make sure that you balance the equation. So we have to put a 2 in front of the chloride ion. So now it is completely balanced. Here's another example of the dissolution of an ionic solid. This is magnesium nitrate. Now, students might be confused because they might not know the difference between monoatomic and polyatomic ions. So some students might break up the magnesium, the nitrogen, and the oxygen into 3 separate ions. But since a polyatomic ion, in this case nitrate, NO3 -1, is different than a monoatomic ion, the reaction should be balanced in terms of both atoms and overall charge. Hopefully you can see that on the right side of the equation, we have a total charge of +2 for magnesium, -6 for the 2 nitride ions, and then -12 for the 6 oxide ions. That's not going to be balanced in terms of charge. So magnesium and nitrate, those are the correct formulas. And again, don't forget to put a 2 in this case in front of the nitrate to balance both the atoms and the charge. All right, here's another example of a substance. And notice that the light bulb is on in this picture, but now it is off. A sample of methanol, CH3OH, is added to water and the solution mixed completely. When this solution is tested for conductivity, it is observed that it does not conduct electricity. Now, students might be tempted when they see OH and they're so familiar with acid-base chemistry, potassium hydroxide, KOH, or sodium hydroxide, NaOH, they might be tempted to break up the formula into a positive and a negative ion. CH3OH is a covalent or a molecular substance. It does not split into a positive and a negative ion like this. We also know that since it was tested for conductivity and it's not an electrolyte, it's going to remain intact. So a covalent or a molecular substance like sugar or water, or in this case, the methanol, if it is soluble in water but does not react with water, it will exist in solution at the particle level as molecules, and it does not dissociate into ions. Now, if we're going to write net ionic equations, it's helpful to know the difference between whether something breaks up into ions or does not. So here are some guidelines for writing net ionic equations. It can be helpful to do the following. Start with a molecular equation in which you simply write the chemical formulas for all of the substances involved, and then you can make the transition to a complete ionic equation. So what that means is split up any chemical formula into ions that should be split up, and then leave together as is any chemical formula that does not dissociate or break up into ions. Then you can cross off what are called the spectator ions, which are the ions that appear on both sides of the equation. And then now you have the net ionic equation. So this second bullet point, the make the transition to the complete ionic equation, you might be asking yourself, well, how would I know whether a chemical formula should be written as is or should it be split up into separate ions? In tomorrow's lesson, I will talk more about different topics of Unit 4, and one of them is topic 4.7, and in topic 4.7, they say specifically that sodium, potassium, ammonium, and nitrate, salts that contain these ions, are soluble in water. But memorization of solubility rules other than these are not going to be assessed on the AP exam. That's a good thing to keep in your head. Sodium, potassium, ammonium, and nitrate, those compounds are always soluble. Something we talked about a week ago, actually a couple of weeks ago, about strong acids and strong bases. There are 6 strong acids, and there are strong bases, which are soluble metal hydroxides, including group 1 and group 2. So these would also be 100% split up into their ions in solution. So in general, how do we know whether we should split the formula up into ions or not? If it is a strong acid or a strong base or a soluble ionic compound, then go ahead and split up the compound into ions in solution. Now, if they say it's solid, you would leave it as a solid. But if they say it's aqueous, dissolved in water, it would be split up. But if it's covalent, like I mentioned before with the CH3OH, compounds like sugar, a weak acid or a weak base would be left together as one formula. A gas like carbon dioxide or oxygen or hydrogen, a pure liquid like the methanol that I mentioned, or other types of pure liquids like water, a pure solid or an insoluble ionic solid would not be split up. So calcium hydroxide happens to be a strong base. That would be split up into ions. Hydrobromic acid is a strong acid that is split up into ions. And in this chemical reaction, we're going to produce water. But water is just a covalent or a molecular substance that's not going to be split up. And it turns out that calcium bromide happens to be aqueous. So again, the AP exam would tell you that by using AQ or saying a solution of calcium bromide. So that would be split up into ions. And like I mentioned before, there are what are called spectator ions. So we have a molecular equation, Ca parentheses OH2 plus 2HBr, and it produces 2H2O plus CaBr2. That's the molecular equation. Now, if I cross off the spectator ions like calcium and bromide on both sides of the equation, I get the net ionic equation. And while this equation might be acceptable on the AP exam, I think just to be on the safe side, if I have the ability to reduce all of the coefficients and still get the lowest possible whole numbers, I should do that. So I'm going to go ahead and divide each of these coefficients by 2. And again, that is my net ionic equation. Let's take a look at a few more examples of converting a molecular equation into a net ionic equation. Here I have H3PO4, which is phosphoric acid. So we saw this equation earlier. We have potassium hydroxide, and it produces water and potassium phosphate. So H3PO4 is not on your list of 6 strong acids, so I would leave that together. Potassium hydroxide is a strong base. Also, it contains the potassium ion, which is soluble. That's a soluble ionic compound. Water is just a covalent compound, and it's molecular. We're not going to split that up. And potassium ions are soluble in ionic compounds. So we have potassium and phosphate. Notice that I have 3 potassiums because of the subscript 3. And on the left side of the equation, I have 3 potassiums because there was a coefficient of 3 in the balanced equation. I'm going to cross off my spectator ions, and now I have that. So on the AP exam, if you had written, for example, the following: H3PO4 plus OH minus to produce H2O and PO4 3 minus. Take a look at what I have just written and compare that with the information at the bottom of this screen. Notice that the ion hydroxide does not have that 3 as a coefficient. The total charge on the left side of the equation is -1. The total charge on the right side of the equation is -3. So make sure that when you are writing a net ionic equation, that it is balanced not only for atoms, but also for charge. All right, here's an example of magnesium nitrate and sodium phosphate. We saw this one earlier. Everything in this particular equation is soluble except for the magnesium phosphate. So nitrate ions are soluble. Compounds that contain sodium is soluble. So we have magnesium nitrate broken up into ions. That will be 3 magnesium ions and 6 nitrate ions. Then we have sodium phosphate, also soluble. We have 6 sodium ions and 2 phosphate ions. On the right side of the equation, we have a soluble compound that's going to be 6 sodium ions and 6 nitrate ions. And again, it turns out that magnesium phosphate happens to be an insoluble or slightly soluble ionic compound, so we're not going to break that up into ions. Once we cross off our spectator ions, that's going to include the nitrate on both sides and the sodium on both sides, we are left with the net ionic equation. So again, had you written this on the AP chemistry exam, magnesium plus phosphate to produce magnesium phosphate, that would be incorrect because the formula of magnesium phosphate is not MgPO4. And had you written the correct formula of magnesium phosphate, but did not balance the equation in terms of the atoms, that would also be incorrect. So watch out for how you balance net ionic equations. All right, so in this example, we have sodium hydroxide and copper sulfate reacting together. And I've told you that they are aqueous with the symbol AQ. On the right, we have copper hydroxide and sodium sulfate. So this section of my lesson is entitled Mistakes to Avoid when Writing Net Ionic Equations. Because I have given you the AQ or the S as a phase of matter, it should be very straightforward and obvious in this case that copper hydroxide is the precipitate because it has an S next to it for solid. So if you had to write the net ionic equation, you would not need to include AQ or S in your answer, but you should recognize that the copper hydroxide is in fact going to be the precipitate, whereas sodium and sulfate, because they are soluble on both the left and the right, sodium and sulfate are the spectator ions. So I'm now going to go through several wrong answers to this net ionic equation. And these are all very common mistakes that we see at the AP reading on the AP exam when students are writing responses to net ionic equations. So pay close attention to these examples and make sure that you can work hard to avoid making these kinds of mistakes. All right, so net ionic equation for the formation of copper hydroxide. So what did this student do wrong? Well, hopefully you can see that they did not balance their equation. Okay, here's another mistake. We're trying to make copper hydroxide. So what did this student do wrong? Well, they have balanced the equation, at least on the left, in terms of 2 hydroxide. That looks good. However, they have written their formula on the right side of the equation without the parentheses. That would also be considered incorrect. So that does not show 2 oxygens and 2 hydrogens without those parentheses. Okay, here's another mistake. Let's see what this student did wrong. They did a good job with the balancing, but the charges on the ions are missing. So again, make sure that you don't fall into these traps or these mistakes. Here's another mistake that a student made. Looks like they have attempted to balance the equation and they have charges on their ions. But if you look closely, the charge on the copper ion should be +2, not +1. So again, pay attention to these little subtle mistakes that students can make. Here's another one that might happen. They have charges on their ions, but unfortunately the signs of the charges on the ions are reversed. So copper should be +2 and hydroxide should be -1. Again, these are all mistakes that students might make. Hopefully you don't fall into these categories with your answers. In this case, it's very clear that copper hydroxide is a solid. So here is another example of a student mistake. They have written a correctly balanced equation for the wrong product. So we know that sodium sulfate is aqueous, therefore it would be split up into separate ions. The product should be the insoluble ionic solid, not the aqueous ionic solid. And then this person tried really hard to get all of the information out there, but this as their final answer would be marked incorrect because the spectator ions were not crossed off on both sides of the equation. So the correct answer would look exactly like this as far as the net ionic equation is concerned. Here's another example of mistakes to avoid when writing net ionic equations. I have a different reaction for you. It says a strip of solid aluminum metal or aluminium metal is added to a solution of copper 2 chloride. The products of the reaction are solid copper and aqueous aluminium chloride. So we have to look at aluminum or aluminium reacting with copper 2 chloride. So there's the correct formula, and that's a solution of, so it's aqueous. And we have solid copper as a product and aluminium chloride, which happens to be +3 for aluminum or aluminium. So we have not balanced the equation yet. We're going to need 6 chlorines on both sides because the least common multiple of 2 and 3 is 6. So we'll balance the chlorides, and then we'll balance the aluminium and the copper. So I have not written the net ionic equation. This is the molecular equation. Let's go ahead and transition to the net ionic equation. Well, here is a student's mistake. They focused on the aluminium chloride, which is AlCl3, and this is what they wrote. It's a fine equation with respect to the formation of AlCl3. It's balanced in terms of atoms and charge, but look at the aluminum or aluminium on the left. The charge on the Al on the left side of the equation is 0. It's not +3. So it doesn't start off as ions, it starts off as atoms. And since AlCl3 is a soluble ionic compound, it would not be written together, but rather broken up into ions. So watch out for making mistakes like that. Here's another mistake that a student made. They have written everything correctly in terms of what should be remaining together and what should be broken up, but they forgot to cross off the spectator ions on both sides of the equation. So again, watch out for that mistake. All right, now I'm going to go ahead and give you another example. We have aluminum reacting with copper ions to produce copper metal and aluminum ions. So do you see the problem here? It is balanced in terms of atoms, but it is not balanced in terms of overall charge. We have +2 on the left and +3 on the right. This is incorrectly balanced with respect to the overall charge. So this one looks really good in terms of atoms and charge. Hopefully you can see what they did wrong. It's a fine equation except for one important detail. It is written backwards. So the aluminum should be on the left in the form of 0 or no charge, and the aluminum ions should be on the right. Copper solid should be on the right, and copper ions on the left. So again, the correct answer would look like this, where the chloride ions have been eliminated. So again, pay attention to how to write net ionic equations, as well as what mistakes that commonly are made on the AP exam, how you can avoid those mistakes. All right, before we get to our homework, I want to talk about particle diagrams. So here is an example of a chemical reaction involving 2 moles of hydrogen reacting with 1 mole of oxygen to produce 2 moles of water. So how would particle diagrams be used to represent this reaction? Well, here is one example. So I have 4 water molecules in the box on the right, and I have 4 hydrogen molecules in the box on the left, and 2 molecules of oxygen in that same box. So particle diagrams can be used to represent the reactants and the products in a chemical reaction. You can see that there is a 2-to-1 ratio between the molecules, just like there is in the coefficients in the balanced equation. So on the left, we have 4 molecules of hydrogen for every 2 molecules of oxygen. Now, you can also use particle diagrams to illustrate the concept of limiting reactants. So in this case, I have not given you exactly a 2-to-1 ratio between hydrogen and oxygen. So here are 2 molecules of hydrogen and 1 molecule of oxygen. That would make 2 molecules of water. Here's another 2 molecules of hydrogen and 1 molecule of oxygen. That would make another 2 molecules of water. So as you can see, we're actually going to run out of hydrogen. I've got another 2 molecules of hydrogen, 1 molecule of oxygen. I've got 2 more waters, but I've got this particular oxygen now is left over. So you could use particle diagrams to indicate the ratio and what might be considered leftover, excess at the end of a reaction. All right, in terms of particle diagrams to represent reactions, here we have silver nitrate, which is a soluble compound, reacting with sodium chloride, also soluble, to produce silver chloride and sodium nitrate. Since sodium and nitrate are always soluble, we have a precipitate of silver chloride in this case, and I'm going to show you that with the phases of matter. So everything is aqueous except for solid silver chloride. All right, here's an example of particle diagrams. A dilute solution, so not very concentrated, of silver nitrate is combined with excess sodium chloride to form solid silver chloride. Which of these diagrams best represents the ions that are present in significant concentrations in the solution? Justify your answer. Well, before we look at these diagrams closely, let's try to get the net ionic equation for this particular reaction. So for the net ionic equation, I'm going to go ahead and split up the silver and the nitrate because it's soluble. I'm going to split up the sodium and the chloride because it's soluble. I'm not going to split up the silver chloride because it is insoluble. That's a solid. And I'm going to split up the sodium and the nitrate. Cross off my spectator ions on both sides of the equation. And here is my net ionic equation with the spectator ions being sodium and nitrate. So what I'm looking for is solid silver chloride on the bottom of this beaker and sodium and nitrate in solution. This looks like a very attractive and possibly correct answer. It's got sodium and nitrate in the solution, still dissolved, and there is the solid silver chloride on the bottom. The only problem with this particular diagram is if I didn't read carefully, I might have ignored this particular phrase, with excess sodium chloride. So what does that mean? Well, what it means is that if sodium chloride is the excess reactant, there's going to be excess left over, and silver nitrate is the limiting reactant. All of the silver ions will have been converted into solid silver chloride. So in terms of particle diagrams, I need to cross off any diagram that still shows silver left over. So all of the silver would need to be consumed, and therefore I can get rid of these. Now down to these 2 diagrams that I have left, as far as which of these diagrams is correct, the excess sodium chloride means that there should still be excess chloride ions present in solution. So that makes this diagram the correct answer. So the correct answer is this one right here because of the excess chloride ions that are present in the particle diagram. The diagram over here would have only been correct if we had exactly the perfect 1-to-1 mole ratio of these 2 reactants. All right, looking at another example of particle diagrams here, we have 1 liter of a silver nitrate solution reacting with 1 liter of a magnesium chloride solution, and you can see particles representing the ions in the diagram. And then that combination produces 2 liters of a final mixture of silver chloride solid, which is on the bottom of the beaker, and magnesium nitrate still dissolved. So we have silver nitrate reacting with magnesium chloride to produce silver chloride solid and magnesium nitrate aqueous. After examining the particle diagram shown above, a student made the claim that the concentration of silver nitrate is the same as the concentration of magnesium chloride. Do you agree with the student's claim? Justify your answer based on the information in the particle diagram. So do not use the balanced chemical equation to justify your answer. Use the specific particles that are featured in the diagram. So do you agree that the concentration of silver nitrate is the same as the concentration of magnesium chloride? This would be a good time to pause the video and see if you agree with the claim before you press play and reveal the answer that I'm about to tell you. Okay, well, if you look closely at the diagram and we start counting the positive ions here, this is silver. That's 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 10 silver ions. Now for the cations, Mg2+, 1, 2, 3, 4, 5. So therefore, I disagree with the student's claim, and here's why. Each of the solutions has the same volume, so they're both 1 liter. But since there are twice as many silver particles as there are magnesium particles, the concentration of silver nitrate should be twice as much as that of magnesium chloride. Another example of particle diagrams, or a question that could be asked about this particle diagram, is the following. A student made the claim that the value of concentration of magnesium in beaker Y, which is the middle beaker, is twice as much as the value of the concentration of magnesium in beaker Z. So do you agree? Justify your answer based on the information in the particle diagram. So do you think that the concentration of magnesium in beaker Y is twice as much as that of beaker Z? Okay, well, if you had a chance to think about that, let me go ahead and tell you the answer. As you can see, we have 5 particles of magnesium in each beaker. So 1, 2, 3, 4, 5. And then we still have 1, 2, 3, 4, 5. So the number of moles of magnesium is the same, but the volume in beaker Z is twice as much. So I would agree that since we have double the volume in beaker Z, that concentration should be half as much. So there are the same number of magnesium particles in each beaker, but since the volume in beaker Y is essentially half as much as that of Z, the concentration of magnesium is twice as much. All right, here's one more quick particle diagram, and then I promise we'll get to our homework. This was a net ionic equation for a reaction between sodium carbonate and calcium nitrate. The products of the reaction are sodium nitrate, which is soluble, and calcium carbonate, which is insoluble, and you can see the solid down here in the bottom of the beaker. Now, if you take a look closely at the language of this question, they mentioned the word excess again, so we'll think about that. All right, the net ionic equation would be, if I see an aqueous ionic compound, let's split it up. I see 2 aqueous ionic compounds, we'll go ahead and split them up. And I see an aqueous ionic compound on the right, let's go ahead and split that up. And then finally, calcium carbonate, they say S for solid, that is insoluble, that's a precipitate, so I'm not going to split that up. Cross off the spectator ions. So part A, write the net ionic equation for the reaction that occurs when these solutions are mixed, and there is your answer. The spectator ions are sodium and nitrate. Now let's focus on that word excess as it relates to the particle diagram. So draw in the species that need to accurately represent the major ionic species, it says the diagram is incomplete. So if the calcium nitrate is the excess reactant, then that means that sodium carbonate is limiting. And so all of the carbonate should be consumed and turned into solid calcium carbonate, but there should be an excess of calcium ions. So many students on this question did this. Well, hey, they wanted to show an excess of calcium ions. So is there a problem with writing 1 versus 2 versus 3 versus 4? Take a look at what I mentioned before about the overall charge. So if you count up all of the ions that are positive in this diagram, we have a total charge of positive 6 because we have 2 sodiums that are +1 each and 2 calciums that are +2 each. But I only have 4 nitrates, and that would be -1 each. So unfortunately, if students put 2 calcium ions into their answer, they did not receive credit because the charge balance was not taken care of. So this would be a correct answer. Only 1 calcium ion should be added because now we have a total charge of +4 and -4 in this diagram. So what if you really want to put 2 calcium ions in that diagram? Well, you could. If you want to add 2 calcium ions, then you'd also have to add 2 more nitrate ions to get a total charge of -6 to balance the +6. Okay, well, that wraps up this particular lesson. We'll now go to our homework. So again, in today's lesson, we talked about chemical reactions as well as physical and chemical change. We talked about net ionic equations, and we took a good look at particle diagrams to represent reactions. So for your homework for tomorrow's lesson, there are 2 screens. I'll go ahead and just pause momentarily so you can get a screenshot of each of these. So this is the first slide, and the homework problem has to do with a chemical reaction involving potassium iodide and lead nitrate. And this is the second screen. So I will explain the answers to all of these questions in tomorrow's lesson. Just a quick reminder about the helpful chemistry resources at the bottom in the video description. Thank you very much for watching. Again, this has been Michael Faribaugh from Albemarle High School in Charlottesville, Virginia. Again, go to cb.org/tech if you or anyone you know needs assistance with mobile tools or connectivity. Thanks for watching.